In this video lecture, we will discuss about single electrode potential and its measurement. Right? By single electrode, we mean this zinc electrode in this electrochemical cell that consists of zinc electrode and copper electrode. This zinc, the measurement of electrode potential of this zinc electrode or this copper electrode, the absolute value of electrode potential of zinc electrode or copper electrode is your single electrode potential, right? And if you remember, we have already discussed this in the previous lecture about electrode potential, right? Electrode potential was oxidation potential and reduction potential. In this half cell in zinc electrode where oxidation occurred, right, and as a result of oxidation, this was the oxidation reaction, right? Zinc lost 2 electrons, right, and formed zinc ions. These zinc ions enter into solution and it made the solution positive, right? So there was a layer of positive charge, right, and these electrons got stuck to this rod, making it negatively charged electrode, right, or negatively charged rod. So this rod was negatively charged and this solution was positively charged when we discussed about electrode potential. Due to this charges separation, there is potential difference that got developed in this half cell. This electrode potential, this electrode potential or this potential difference was called as oxidation potential because this resulted as a result of oxidation reaction. Similarly, in this half cell, the electrons lost by zinc was gained by copper ions in this solution, right, forming copper metal, right? So this copper rod became positively charged due to the deficiency of electrons because copper ions took electrons from this rod, right, making it electron deficient, positively charged. And since there are sulfate ions, right, in this solution, and copper ions become less, right, as the reaction goes on, so the solution became negatively charged due to these sulfate ions and rod was positively charged. So again we have charge separation due to which potential difference exists in this half cell. This potential difference was termed as reduction potential because it occurred due to reduction potential, right? So here was oxidation, right? Here in this half cell oxidation occurred and in this half cell reduction occurred, right? So now suppose if we want to find the electrode potential of this zinc electrode, right, would we be able to find its electrode potential, which is called as single electrode potential, right, without copper, right? Without copper we would not be able to find the electrode potential of this single electrode, which is zinc electrode, because when zinc lost these electrons were gained by copper, right? So this reaction, we know that in chemical reaction transfer of electrons takes place, right? So when we don't have copper, because it's copper electrode that accepted the electrons lost by zinc electrode. No copper electrode means these electrons would not be accepted, right? And moreover, this tendency of zinc to lose electrons is a relative tendency, right? And it lost electrons in the presence of copper electrode because copper has high reduction potential and zinc has high oxidation potential, right? So zinc lost electrons and these electrons are gained by copper, thereby completing the chemical reaction, right? So now if we just have this half cell which consists of zinc electrode, right, then zinc electrode would not undergo oxidation, right, because oxidation cannot occur without reduction, right, and reduction cannot occur without oxidation. Suppose if I remove this zinc electrode and if you try to find the reduction potential of this copper electrode, then the reduction potential of copper electrode was due to the gain of electrons, and these electrons came from zinc electrode, right? So without zinc, the reduction would not take place in this half cell, right? So you would not be able to find the electrode potential of these electrodes, right, without the other. right? These electrode has to be there together to find their electrode potential. Now just recall one thing, right, to understand this better. We have already discussed in the first lecture, if you remember, this was the zinc rod, right? We put the zinc rod in copper sulfate solution, right? And this was the reaction that took place. Right? So here zinc lost electrons, right, to form zinc ions, and this copper gained these electrons to form copper metal. So if I remove zinc, removing this half cell means it's like removing zinc. So if we don't have zinc here, then this copper sulfate alone would not be able to do anything. It would not undergo this reduction reaction, right, without zinc, right? Because it is zinc that gave its 2 electrons to copper to reduce, right? Similarly, if I remove copper sulfate, that is copper ions, then zinc alone would not undo oxidation because there is no one to give electrons, right? So oxidation and reduction occur together, right? That is why we say that it is impossible to determine the absolute value of potential of single electrode, because it is impossible to have either oxidation or reduction without the other, right? So oxidation and reduction always occur together, not alone. If I remove this zinc electrode or copper electrode, there would be no oxidation and reduction. No oxidation and reduction means no electrode potential. But still, if we want to calculate the single electrode potential or the absolute value of electrode potential of, say, zinc or copper, right, then what we can do, right? We have discussed about standard hydrogen electrode before this lecture. Standard hydrogen electrode, we know that under standard conditions of temperature, pressure and concentration, the electrode potential of this standard hydrogen electrode was 0 volt, right? And this standard hydrogen electrode can act as anode as well as cathode, right? Now what we do is, if we want to calculate the standard electrode potential of, say, zinc electrode, what we do is we couple this standard hydrogen electrode with zinc electrode, right? And we will find the EMF of the cell that is formed by coupling zinc electrode with standard hydrogen electrode, right? And since we know that the electrode potential of standard hydrogen electrode is 0, right? So whatever is the potential difference or the EMF of the resulting cell, or which we get in the reading of the voltmeter, right, whatever is the EMF, right, is the electrode potential of the electrode under investigation, right? That is zinc electrode, because the electrode potential of standard hydrogen electrode is 0, right? So if we look at the formula of EMF of the cell, it was ER minus EL, standard reduction potential. And whatever calculations or whatever discussion we are doing for electrode potential here, we are doing this under standard conditions, right? Standard conditions means, by standard conditions we mean temperature 298 Kelvin, pressure 1 bar and concentration as 1 molar. These are standard conditions, right? So now the standard reduction potential of right hand cell, that is cathode, and this is standard reduction potential of left hand cell, that is anode, ER minus EL, right? So whatever value of EMF that we get for this cell, right, is due to the oxidation and reduction potential, that is happening in these two half cells, right? And these are relative to one another, right? Suppose you have zinc electrode, so as soon as you set up copper electrode in the other half cell, it will set up its own potential, right? So the potential difference in the two half cell is relative to one another, right? So from here also you cannot find the value of electrode potential of single electrode, right? So what you do is, now since this is the formula for EMF, that we have already calculated, right? We have already derived this in the previous lecture. Now also, when you couple this electrode under investigation with standard hydrogen electrode, the EMF that you get from this formula would be the EMF of this, or the potential difference of the electrode under investigation. And the second thing that we need to look upon is direction of flow of current. Direction of flow of current, right? Since we know that current flows from cathode to anode, right? So electrons will flow in direction opposite of current, right? So electron flows from anode to cathode, right? And this deflection of this voltmeter will tell us the direction of flow of current, and from the direction of flow of current we will get to know the direction of flow of electrons, right? So from if electrons are flowing from, say, electrode under investigation, right, to standard hydrogen electrode, right, then this electrode would act as anode and this would act as cathode, since electrons are moving in this direction, right? And if, say, you have standard hydrogen electrode in this direction, right, and you have, say, you have copper electrode in the right hand cell, right, this is your copper electrode, and direction of flow of current again is in this direction. That is, this time electrons are flowing from standard hydrogen electrode to copper electrode. In that case, standard hydrogen electrode would act as anode and copper would act as cathode, right? So here SHE is acting as anode and here SHE is acting as cathode, right? And this depends upon the relative tendency of the other electrode, right? So, and we have already discussed in the previous lecture that standard hydrogen electrode can act as cathode and anode, right? So suppose I create this cell. Suppose here I have this zinc electrode, right, and here I have this SHE, standard hydrogen electrode, right? And what we do is we join these two via this wire, and there is a voltmeter, right? And this deflection of voltmeter will show you the direction of flow of current, right? That means electrons are flowing from, if direction of flow of current is from SHE to zinc, then that means electrons are flowing in this direction, right? So here this zinc is acting as anode, right? Since electrons are flowing out of it, that is, oxidation is taking place, zinc is losing electrons to form zinc ions, right? And SHE will act as cathode, right? So direction of flow of current will tell us which is anode and which is cathode. Direction of flow of current or direction of flow of electrons will tell us which is anode and which is cathode, right? And the EMF of this cell was found out to be 0.76 volt, right? And the direction of flow of electrons is from zinc electrode to the hydrogen electrode, right? So this is the reading of the voltmeter, right? So since we know that potential difference or electrode potential of standard hydrogen electrode is 0, right? So whatever reading that we got in the voltmeter is due to zinc electrode only, right? So we say that electrode potential or oxidation potential, since what is occurring here? Oxidation is occurring here, right? Oxidation is taking place here. that is zinc is losing 2 electrons to form zinc ions, right? Oxidation is occurring here, right? So this is your oxidation potential of zinc electrode. Or since IUPAC says that we always mention electrode potential in terms of reduction potential, right? So reduction potential of zinc would be minus 0.76 volt, right? This is the reduction potential of zinc, since this does not participate because of its zero value, right? Similarly, if we talk about this scenario, right, where anode is the copper electrode, right, and cathode is your standard hydrogen electrode, right? So what we do is we just put this standard hydrogen electrode here, right, and we connect to it this copper electrode like here. Yeah, this is your copper electrode, right? And we have a voltmeter over here, right? And we'll see the deflection of this voltmeter, which would be like this, in this direction. That means current is flowing in this direction, right? That means electrons are flowing from, this is your SHE, right? Electrons are flowing in this direction. That is, electrons are flowing from SHE to copper electrode. So SHE would act as anode here and copper would act as cathode, right? And the reading of this voltmeter or galvanometer, reading of this voltmeter would be your 0.34 volt, right? So since we know that standard hydrogen electrode potential for standard hydrogen electrode is 0, so this reading is alone due to this copper electrode, right? So we say the electrode potential of copper is 0.34, right, which is its reduction potential, since reduction is taking place at copper electrode in this scenario, because this electrons are moving towards copper, right, and copper is gaining electrons, right? So copper here is acting as cathode, right, due to gain of electrons, and these electrons are lost by the standard hydrogen electrode. So at SHE, this reaction would take place. It will gain 2 electrons and form hydrogen gas. These 2 electrons will move to copper electrode, and copper ions will gain these electrons to form copper metal, right? So this is the concept of calculating the standard electrode potential of single electrode, right, using standard hydrogen electrode, right? When you couple, what basically we are doing is, to calculate the standard electrode potential of any electrode, we couple it with